Okay, so our first item back after our long break here is something called the mean value theorem. Now, the mean value theorem is not something that you need to worry about in terms of, is there a problem I can do? Is there a value? Is there an answer I can get? The mean value theorem is more of a theoretical notion. So this particular discussion here is going to be about a theoretical idea that is going to be the foundation for several of the things we'll be doing later on. So the mean value theorem says this. It says that if f of x is continuous on the closed interval AB. Now, let's remember what continuous means. Remind ourselves, continuous means we have no holes, no jumps, no vertical asymptotes. So the function is continuous on the closed interval, and we also require that it is differentiable on the open interval. Let's remember what that means. Differentiable means the derivative exists, and for our purposes, what that means is there are no cusps. The graph never comes to a point. So the function is continuous on the closed interval, no holes, no jumps, no vertical asymptotes, and differentiable on the open interval. That means there are no cusps. Any function that meets these two requirements is what we call a smooth curve. So if the function is continuous on the closed interval, differentiable on the open interval, then, and what I'm going to do is I'm going to leave off the statement of the mean value theorem because when you first see it, it doesn't seem to make a lot of sense. It's a little bit hard to understand what's going on. First, what I'm going to do is I'm going to draw the picture. I'm going to say in ordinary people words what that means, and then we're going to write that down in terms of the mathematics. So, here's our value A and our value for B. And so let's suppose this is f of A and this is f of B. And the curve must connect those 2 points, must have no holes, no jumps, no vertical asymptotes, and it must not come to a point. So let's suppose it's something relatively straightforward like that. So that's a curve that connects those 2 points that meets these 2 requirements. The mean value theorem says this. There must be somewhere on this curve a tangent line, a point of tangency and a tangent line that is parallel to this line. If you connect the line or connect the points A comma f of A and B comma f of B. Let's write that in. So the coordinates of this point are A comma f of A. That's the coordinates of this point. And this point has coordinates B comma f of B. If you connect those 2 points, that is, remember from earlier in the semester, that is a secant line. The mean value theorem says somewhere on this curve there must be a tangent line that is parallel to that secant line. There must be a tangent line somewhere on here that is parallel to this blue line segment I've drawn here. And within the limits of my not very well drawn picture, it looks as though that is approximately the point we're looking for. The mean value theorem says there must exist a value C between A and B. The C must be between A and B. It must be in this open interval. And at that point, this point is C comma f of C. At that point, the tangent line is parallel to the secant line. That must be true no matter what curve we start with. Now, when we say there must exist a point, remember what we mean is there exists at least one. There may be multiple points. There may be more than one point where the tangent is parallel to the secant. A picture like this, suppose this is A, this is B. F of A, f of B. Suppose the curve is that. Well, here's our secant line. There must exist at least one. There may be more. In this case, there are more than one. There's more than one. But there must exist at least one point where the tangent line is parallel to the secant line. So in this case, there's one possibility. Let's call that C number 1. There's another possibility. There's C number 2. There's another possibility, C number 3. So in that particular case, there are 3 points where the tangent is parallel to the secant. Why that's important, we're going to kick down the road for a little bit. But for now, all we're saying is the mean value theorem guarantees the existence of this point C, and it guarantees that at that point, the tangent line is parallel to the secant line. Now let's translate that into some calculus. The slope of the tangent line is equal to the slope of the secant line. That's what we mean by those two being parallel. So what we're saying is there must exist a C, there must be a value of C, and for that value of C, the slope of the tangent line must equal the slope of the secant line. All that remains for us to do is to write that statement down in official mathematics. So, the mean value theorem says, if a function is continuous on the closed interval, it's differentiable on the open interval, then there is a C, and remember, there's at least one, there may be more than one, but there's at least one value C in the open interval A, comma B. So remember what this means. C is not allowed to equal A, C is not allowed to equal B, but it must be somewhere in between. There exists a C in the open interval, and then what must be true there? The slope of the secant line, the slope of the tangent must equal the slope of the secant. Now, we know how to write that in terms of the mathematics. The slope of the tangent line at this point. Well, the slope of the tangent line is calculus code for the derivative. So when we say the slope of the tangent line there, what we mean is the derivative evaluated at C. So this phrase means the derivative of f evaluated at C. That's what we mean by the slope of the tangent line. And we know how to write the slope of the secant line because the slope of the secant is given by the change in y divided by the change in x. And so I'm going to write this over here. F prime of C is equal to, I need the change in the y coordinates from here to here. That's f of b minus f of a, divide by the change in the x coordinates from here to here. That's b minus a. And that is the conclusion of the mean value theorem. Let me see if I can sort of pull this together. I'm going to erase my picture. The mean value theorem says, if the function is continuous on the closed interval and differentiable on the open interval, then there exists a C in the open interval such that, and the requirement is f prime of C is equal to f of b minus f of a over b minus a. What does that mean? There exists a C in the interval such that the slope of the tangent line at that value C, f of C, must equal the slope of the secant line. Again, here's our picture. I've been drawing my f of a little bit lower. It doesn't matter what a and f and b are. It doesn't matter where f of a and f of b are. So it could be that f of a is higher f of b is lower, but any curve that connects those two, there must exist at least one, maybe more, but there must exist at least one point between A and B such that the slope of the tangent line, that's what this means, the slope of the tangent line is equal to, that means these are parallel, the slope of the secant line. That's what this represents. In this particular case, it looks like we had a couple choices for our value of C. We could have chosen this to be C, I'll call it C number 1. We could have chosen this to be C, I'll call it C number 2. There's no guarantee that there will be 2 or 3 or more, but it does guarantee there must be at least one. So that's the mean value theorem. From your side of the video, what do you need to understand? Just be familiar with it. Later on, I'm going to use this as the foundation to make a new argument. And when you see that happen, you should be familiar with the mean value theorem. I'm going to pull this expression out of the air. It doesn't come out of thin air, it comes out of this mean value theorem. In the interest of time, we're not going to go through a proof of this. It's not particularly challenging, and it is actually written in the text if you really feel like you want to read through that. But for now, we're going to accept this as a proven theorem, and then we'll be able to use it later to find some other, to work with some other information.